Here we see again the 8 disciplines as given by Elmar Federer. And we're going to start with the first 0 discipline, become aware of the problem, prepare and plan. So just to recap from the define part of this series, a problem is a deviation of a required attribute in the product, the output of a process, to an agreed requirement or specification. So in other words, a problem is simply the difference between what you have and what you want. So in this 0th discipline, you may find out that you have multiple problems that all seem to be urgent. And the task here is to identify the problem or multiple problems and sort these problems. Determine the importance and the urgency. Is this a crisis? Do we need a task force? Do we even need an 8D? Do we have to inform the customer? And here we need to make sure we don't underestimate the problem or the time that will be taken to solve the problem. Now, common tools, as we've seen before, you can use something like the Pareto analysis to select and prioritize the topic, but generally what happens is that there's some data that has indicated that there's a problem, and so looking at this data will give everyone a clear picture that something needs to be investigated. Now, then you want to grab a team, and very briefly, team leader should be someone who has the right expertise to solve the problem, generally the owner of the process or the area where the process occurred. And so this person is responsible for meeting any requirements and expectations of the organization or from external customers. For example, like how fast the problem should be solved. An 8D moderator, on the other hand, is preferably not an expert. I'll put here, this is more the expert, the area leader, not an expert. This person needs to be trained in the 8D methodology. This person needs to support the team by guiding them through the 8D and giving feedback, being open-minded. A sponsor, on the other hand, is responsible, also known as a champion, responsible for resources. They also need to provide leadership if it's necessary. They will support any final decision making and give the authority to implement any corrective action. And then finally, the most important is the team members. These are people that really are the experts assigned to work on the problem with their specific knowledge. And they then need to work, so we'll have experts, specific knowledge. They need to have the time allocated and the resource allocated so that they can work on the problem, and they need to work within the constructs of the 8D so that this can be resolved in the proper manner. Now, understand the problem. We have our burnt cookie here. Our output is not as we expected. And often the way this starts is that you start asking the questions who, what, where, when, why, how, and how many. Now, for an 8D, typically what is important is where, and this means where was the problem found. So which site, which location, which product line, and then also where on the product. And this can be, we'll see in the next slide, example of, is it all over the product or in part of the product, or if there's several products processed together, is it just part of that batch, for example? The other important question in 8D is when. When was the first occurrence? When is the first occurrence? And is there any type of time pattern to the defect? Do we see it reoccurring every cycle, every day, every shift, for example? And then, of course, how many products are affected? That's very important because of the containment step. And all of these answers have to be based on facts. No guesses. So here's an example. This is a DRAM, dynamic random access memory, and it's very, very old. This is a silicon wafer with DRAM chips on it, and green is good and black is bad. So what we see is at the end of the processing, these chips had low yield at 9 o'clock and 3 o'clock. So we identify our problem, we see the problem. Now we are interested in, is this going to be, is this urgent? Does this affect our shipments? How fast do we need to danger for the reliability issue for the other customers? And in this exact example, for people that remember this old technology, we had these trenches here, these deep holes in the silicon, and this line was supposed to be aligned with these holes, and it wasn't. That was the problem. But that we come to later. So we need to understand, we need to first see that there's a problem. Here we have low yield loss. Now, you need to take containment actions. In this step, we want to define and implement any containment actions that will protect the customer from the problem. Now, this could be a quick fix. For example, stopping a machine that's not working. Stopping all the product that was processed on that machine so it doesn't reach the customer. And here's sort of the example of where you can see that there's a problem, and they've already gone one step further. We have here time, and we have here products that are measured periodically. And what we see is we have 5 different machines, NS22, 23, 24, 29, and 31. And here we see 29 with the diamonds, the orange diamonds. And what you can see is starting at a certain point of time, there's one here, then it seems to be okay. But basically, from right about here to here, this certain time period, everything that was processed on NS29 is giving a crazy signature. It's not where it's supposed to be. So here we know any parts that are processed on NS29 in that period are likely to have a problem. And here I drew a picture of it. You have different process steps coming here. All of this product is good. And then the product goes through different machines, and anyone that happened to hit NS29 will then continue and end up going out the door, shipment, if there's no containment action. So parts that are processed through machine NS29 after a certain time or between a certain time period or in a certain time period are defective. These parts need to be contained. So the targets of containment, you need to protect the customer. Limit the number and severity of fails. And the worst case, you have to predict the failure rates of material in the field. And here we have more management involvement. Do we need to talk to the customer? How is that going to be communicated? You also want to limit the impact on the company. You want to limit the damage on the WIP. You don't want to produce any more parts on this NS29 because everything that goes into that has to be scrapped. So everything earlier would have been wasted. You're also interested, once you get rid of these parts, can you meet your deliverable goals? Are you going to be able to ship what you promised to ship? And then finally, a more tricky part is you want to balance the cost effectiveness. Here we're not sure perhaps if there would be, on my example for the yield, there was definitely a problem, but in some cases you're not sure. Should we wait and do some more tests and hold those parts before shipping them out? And that becomes then a complicated planning question, because if you're holding them, you're not sure if you can count on them, but you're not sure if you should start new material. So the next step then is finding the root cause. And we've done this before. We've done this when we were developing hypotheses. We had a fishbone diagram. We were looking at data for regression and correlation, looking to find out what could be the root cause. Brainstorming here Two other methods are the fault tree analysis and the is not analysis. Just very briefly, fault tree analysis is similar to the 5 whys, sort of a top-down deductive approach where you say, well, there was a problem. What event caused that problem or could have caused that problem? And then one step lower, what events could have caused those events? The is not analysis is taking this idea of the questions, for example, asking where is the problem? Remember we did where, why, what, how many. You say where is the problem? And then on the other side you say where is not the problem. And what you're doing with this type of analysis is setting some boundaries for yourself. You're providing comparisons. So you're saying, well, if the problem is all on product A and it's not on product A, B, and C, what caused the difference between the is side and the is not side? So you've brainstormed and then develop, again, as I said, hypotheses and confirm these with data. So here we've actually already done part of that, right? We've already looked at our data. We've hypothesized that, or we've partially proven that NS29 is producing bad parts. We need to go a little bit further and find out what actually happened. And here we can see from a failure analysis that this particular piece of equipment, these are some electrical devices, and there was actually a short. Now, and again, why did that happen on that particular tool? That's the goal of the root cause. Now, once you've done that, you need to choose a corrective action. So here we want to remove the root cause and the cause and effect link. So here we go. We've got our short due to that tool. We look again maybe at our cause and effect tree. Now here, example, we have scratches on the surface of a material. We look through our fishbone diagram, and for example, we've noticed that we use soft material. So very prone for scratch. And we also notice that we do a lot of manual handling. So for corrective actions, we could consider, for example, changing the material. We used a new material that was not as soft. That would then remove the cause. We would use a new, harder material or scratch-resistant material. On the other hand, we could also, for example, put a protective coating on the surface. Now that would require an extra process step. But a protective coating then would completely remove the link between any type of manual handling and the scratches. I mean, going further could be some kind of, robot handling, automation. So, which of course increase in cost. But the goal here then is to remove any cause and effect link completely.